Okay. Yeah, so thank you very much for the opportunity to participate in this event. So I just wanted to tell you a little bit what's going on over in the theory group in trying to connect quantum field theory, which is just the theory framework for understanding relativistic quantum mechanical systems, with real-world experiments. So next slide. So first, I just wanted to emphasize why, as a theorist, we care about the progress going on in the theory world. And so, of course, the reason the kind of modern era is very exciting as a theorist is we have all these amazing experiments which are really pushing the boundaries of what is possible, both from the precision frontier and just from the sheer amount of data. And so unfortunately, I don't personally own the shirt, but this is my grand advisor who likes to emphasize that even though we don't have the license to push the kind of boundaries on the engineering side, that we should be pushing the boundaries on the theory side. And so one thing which I think is important to emphasize is that a lot of the questions which are kind of very popular in modern theory are really motivated by advances in our ability to measure things on the experimental side. And so nice examples of this are in collider physics. We have the mathematics and physics of scattering amplitudes. There's been a huge advance in what is measurable and computable in cosmology. In the condensed matter physics side, this has motivated advances in the conformal bootstrap. And most recently, measurements in gravity have really pushed both pure mathematics and quantum field theory in trying to understand gravitational scattering amplitudes. Next slide. So just as one of these four, because I'm only supposed to have 5 minutes, so a lot of the work in the theory group is going to try to understand collider physics experiments. And so these are experiments which are trying to study a specific quantum mechanical system, namely the standard model of particle physics, which seems to work very well in describing physics down to very short distances. And so to be able to measure things at very short distances, we need to go to very high energies, which is why we need these extraordinarily large collider physics experiments. And so the kind of game of these collider physics experiments is to try and extract an understanding of the underlying microscopic physics, which goes on in the middle, from these kind of very complicated asymptotic sprays of energy. And so you can think about it kind of like the cosmic microwave background, where you're trying to measure some correlations and learn about what happened in the actual collision. Next slide. And so this is something which has an extremely long history, so it's actually 50 years, last year, I guess, of trying to use these patterns of energy flow to learn about the underlying microscopic theory. And so this is something which is also being pushed hugely by the experimental capabilities. And so the first and most kind of famous example of this, of relating the kind of macroscopic pictures to the underlying microscopic physics, was the discovery of the gluon. And so at this stage, you can just kind of do it by eye. So there's this kind of picture over here where you have this microscopic process, and you can just kind of point by eye and see, oh, there's a gluon. But with the modern LHC experiments and the ability of the experimentalists to measure extremely precise quantities, it's really pushed us on the theory side to have to understand the kind of underlying theory of these experiments. Next slide. And so this is what we do over in the theory group. So this is our kind of abstraction of a very complicated collider physics experiment. So we like this little picture up here, where what we do is we kind of excite some system with a hammer, which we in theory world like to think of as some set of operators. And actually where a lot of the progress has been on the theory side is in understanding the so-called detectors, which are like sensors, or the kind of theoretical description of these camera operators. And so I won't go into any of the technical details in any sense, but a lot of what we've been able to do is understand kind of the quantum mechanical system of these actual detector operators. So we can take detectors, and at least in the theory world, we can like multiply them or say they're commutators. And we have a very nice mathematical machinery for connecting what is actually done in an experiment with the underlying theory. And so in particular, we can take, for example, correlations measured in some very complicated experiment and reduce it to some nice mathematical expressions, which we can study and understand precisely. Next slide. And so then my nice colleagues over Ananya and Andrew have actually gone out and measured these correlation functions. And so this is just an example of a 2-point correlation function of two of these camera operators as you bring them together in angle, which you can really do in the experiments. And so these allow you to actually map out at a very precise level. So not just saying, is there a quark or is there a gluon, but you can actually measure kind of critical exponents of the interaction of the quarks and gluons in one regime over here. And then you see this nice break where they transition from being quarks and gluons into hadrons, and you have the confinement transition, and then they just interact as kind of free particles coming out of your detector. And so using these huge experimental advances and the advances on the theory side and interpreting them, we can actually kind of ask very precise questions about the underlying quantum mechanical systems. Next slide. And so this is just, I'll be very quick, but this is something which is now being studied in a wide variety of different climates across particle and nuclear physics. And it's a very nice opportunity to use this nice theory to interface with kind of questions about real quantum mechanical world studied in colliders. Next slide. I'll just conclude with this overview of other quantum mechanical things that are studied over in the hydrogen theory group in Sloan. Thank you.
Thank you. Any questions? You had a slide that showed the application solar colliders and other systems.
Yes, yeah.
Number 7, I think.
Yes.
So can you say a few words about what you expect will be the next signature measurements that will come out of colliders?
Absolutely, yeah. So one of the big interests of the group over here is to study the relativistic or the quark gluon plasma. And so this is something which is very complicated from the theory side. And so one excitement is trying to back up from the very, very complicated setups of lead-lead collisions where you expect to see something to simpler systems. And so one very recent thing, which was just shown at the Quark Matter last week, was measurements of these in slightly smaller systems. And so this is like P-lead. They're also doing oxygen. And so these are something where you can try and actually understand them from a theory perspective. So these are a bit too hard. You can kind of qualitatively understand what's going on, but they're now kind of backing back down and trying to understand these in simpler systems where you can really have a kind of qualitative or a quantitative understanding across different systems.
I have a quick question. This is David.
Yeah.
Can you go back to the picture with the hammers and the cameras?
Yeah.
All right. So what? Oh, I couldn't quite see it from here, but it looked like you were hitting the camera with the hammer in the picture.
Okay. So it's supposed to be hitting the center with the hammer, and then you detect things with the camera.
Okay. All right.
And the camera is supposed to be very far away.
All right. I was a little confused by that. Thank you very much.
Yeah.